And so we're back to Chapter 6. In this video, we're going to talk about direct and back titrations. Let's get started. This entire video should be a review to you guys. Maybe the last part will be something that's new, the back titration, but volumetric analysis we've seen in general chemistry over and over again, so we should go through this very quickly. So what is a titration? It's a procedure in which increments of known reagent, which is called the titrant, that's the stuff in the burette, is added to the analyte, that's the stuff in the Erlenmeyer flask, until that reaction is complete. So each increment that you drop from that burette should be completely and quickly consumed by the analyte. Of course, until that analyte is used up. The common titrations that you probably have heard of or have seen before are acid-base titrations, or even oxidation and reduction titrations, but there's a bunch of other different ones like precipitation reactions or complex formation titrations. We're going to start out with acid-base titrations, just like in general chemistry. So there's several methods that we can determine if the analyte, the thing in the Erlenmeyer flask, it has been consumed. You can test it by voltage, or a change of color, or maybe just monitoring the absorbance of light in the analyte. Some terms that you should remember are, number one, indicator. That's a compound with a physical property, usually color. That's the one that we used in general chemistry. Phenolphthalein was the indicator. That changes abruptly when the titration is complete. So for example, phenolphthalein from general chemistry would be colorless in acidic solution, but once it became a basic solution, it would turn bright pink. And that's how you would know that reaction was complete. The equivalence point, that's the exact point where titrant equals out analyte. So stoichiometrically, that's exactly how much is needed for the titrant to equal out with the analyte. Of course, this is ideal because more than likely we're going to surpass that point. The endpoint is what we're most accustomed to. The endpoint is that sudden change in physical property that we see, for example, the color change. We don't exactly see when the exact stoichiometric proportion of base equals the exact stoichiometric proportion of acid. But we do see a color change, and that's what's considered the endpoint. Of course, the better your eyes, the closer to the equivalence point you will be, but that's not fair, right? So there's other things that we could do, like I said before, you could do pH, you could do absorbance of light, all this other stuff, but the more careful you are, the closer, hopefully, you'll be to the equivalence point. What is titration error? Well, that's just the difference between the endpoint and the actual real equivalence point of the reaction. What's a blank titration? That's any titration that's carried out without the analyte. So some more terms that we need to be familiar with is primary standard. Primary standard is a reagent that's pure enough to weigh out and use directly to provide a known number of moles. The validity of this type of procedure or titration, it really depends on knowing the amount to high accuracy of one of the reactants. So for example, if you wanted to titrate an unknown concentration of hydrochloric acid with base, you could theoretically weigh out the primary standard grade sodium carbonate and dissolve it in water to make the titrant. Quick question, why shouldn't you use NaOH to carry out this procedure? If you remember, this is exactly what we did in general chemistry. In general chemistry, we had to standardize NaOH. The reason you can't use NaOH is because NaOH is hygroscopic. So what does that mean? That means it absorbs water from the air. So as you're weighing it out, the actual NaOH starts getting mushy because it's starting to absorb water. So however much you think you're weighing, it's probably not what you really weighed. So by the time that you make your calculations and you actually use that NaOH and make your titrant with it, you might, the molarity that you think you have, you might be wrong. So that's why you cannot use NaOH. But what we did do, or what we could do, is standardize the NaOH. So let's talk a little bit about primary standards. Primary standards should be 99.9% pure or better. You want to know as much as you can about this standard. You want to know exactly, almost to the T, how much it weighs, what's its density, everything that you need to know. It shouldn't decompose under ordinary storage, obviously, and it should be stable when dried by heating or vacuum, because drying is usually required to remove any traces of water that's absorbed from the atmosphere, like that NaOH. So lo and behold, titrants, which we use for titrations, are usually not available as primary standards. What a bummer, but that's just the way it is. Instead, a solution that has approximately the desired concentration is used to titrate a weighed primary standard. Ergo, exactly what we did in general chemistry. NaOH, we calculate its approximate desired concentration, and then we use that against a primary standard to figure out what its exact molarity was. And that process, of course, of titrating a standard to determine the concentration of the titrant is called standardization. Some more terms. So what's a standard solution? That should be easy. It's a solution that's concentration we know exactly. So after the standardization process, now we have a standard solution. What's a direct titration? Well, that's pretty easy because that's the normal titration that everyone is exposed to first. A titrant is added to the analyte until an endpoint is observed. So you have your unknown, which is your analyte, you have your titrant, which is in the burette, and that's your known, and you get a product. And then you can kind of calculate anything you need. Once that titration is complete, you can calculate anything you need about your analyte. Well, what's a back titration? A back titration is when a known excess of a standard reagent is added to the analyte. And then a second standard reagent is used to titrate the excess of the first reagent. So for example, you have your analyte, which you don't know. You add a reagent, which you know a lot about. You react those two together and you get yourself a product. Now you know that in this product there's going to be excess reagent because you went ahead and put in excess reagent of that first reagent. So you know that you have your product, but you have an unknown quantity of that excess reagent. The reason it's unknown is because you don't know what your analyte is. So you don't know how much is left over. You don't know how much reacted. Then what you do is you take that excess reagent and you titrate it with another reagent, which you also know a lot about, and that gets your product. If you know how much excess reagent is titrated from that second back titration, then you can back calculate how much original analyte was in your unknown. Now, why on earth would people do this? Well, really simply, it's useful when the endpoint of the back titration is clearer than the direct. Okay, sometimes the direct titration is not really that good. It's not really easy to see. So they use this method. They react something with excess, a known excess amount, and then they use that to titrate with another reagent that they can see easier. And then also when an excess of the first reagent is needed to completely react with the analyte. Of course, if you use excess of the standard reagent in that first reaction, you're going to ensure that complete reaction of the unknown. You're going to ensure that all of it is used. Let's do a simple titration calculation to ensure that we understand the basic concept. Consider the titration of an unknown chlorine solution with standard silver ion. So you've got your silver ion plus your chlorine ion is in equilibrium to make this precipitate, silver chloride. The reaction is fast and the equilibrium constant is really large. So the reaction essentially goes to completion with each addition of your titrant. Suppose that 10 mils of the unknown chlorine solution requires 22.97 mils of a 0.05274 molar silver nitrate solution for complete reaction. What is the concentration of the chlorine in the unknown? So where do I go? I want to know the concentration of chlorine. They give me all the information about silver nitrate. So why don't I go ahead and find out how many moles of silver nitrate, because then I know that it's a 1-to-1 ratio. Look at the reaction up here. So all I do is 0.02297 liters times 0.05274 molar or moles per liter of silver nitrate. That gives me moles of silver nitrate. In essence, that is the moles of silver, and I know that I have a 1-to-1 molar ratio of silver to chlorine. So therefore, I take that and I divide it by 0.010 because that's how much volume of the chlorine was used. So if I do that, I should get, or you should get, 0.1211 molar. As I said, this was a really simple calculation, and you are expected to do harder ones. That's why you need to practice every single problem in your book. Let's move on. Now that we know KSP, solubility products, and we know about titrations, we can talk about things like this. So silver iodide has a really small solubility product than silver chloride. So when you add silver ion to a solution of chlorine ion and iodine ion, that AgI is going to precipitate first. Why? Because it has a smaller solubility. Now, because those two solubilities of those two reactions are significantly different, I mean, one's 10 to the negative 17th, the other one's 10 to the negative 10, that first precipitation is almost nearly complete before the second one actually starts. So look here, where it says curve B, that is the titration that's happening with AgI, because you notice that B, look at the voltage down here. The equivalence point of that AgI reaction happens at around 23.85. If you look at the insert right there, they tell you how they calculate that endpoint. So that first reaction is completely done. It's complete before you even really start the second reaction, which is the AgCl. You notice that the chloride endpoint is way, way different. It's like 47.41, which is right over here. So this is how you can titrate a mixture of solutions. Now, realize that for this to be useful, like I said, they have to be, their KSPs have to be sort of different, because if they're really close to each other, that obviously is going to make it harder. Let's extract some results from this titration curve. In curve A of the previous titration, 40 mils of an unknown solution containing both iodide ion and chloride ion were titrated with 0.0845 molar silver ion. Find the concentrations of each halide. Of course, the halides are the iodine and the chlorine. Let's go back to the curve and see if we can figure out what they want. Let's try first to reason with this. So we know where the first endpoint is. The first endpoint is at 23.85. We know that everything here is a 1-to-1. So for example, 1 mole of iodine is going to consume 1 mole of silver ion. And the moles of Ag plus that were delivered at this point, at the first titration point, would have been 0.0845, which is the molarity of the Ag plus, times how much volume it took to get to that endpoint. So it would be 0.0845 times 0.02385. That'll give you the molarity, the number of moles of Ag that were delivered. And that happens to be 2.015 times 10 to the negative 3 moles of Ag plus. Now, the molarity of the iodide in that unknown solution would be the number of moles divided by the volume that the solution had. So it was 40 mils. So you take 2.015 times 10 to the negative 3 moles divided by the 0.04000, and that'll give you the molarity of the iodide. How do we figure out the concentration of the other halide, the chloride? We know the second endpoint. The second endpoint is 47.41. And we know how much Ag plus was required to react with the chlorine, because all it would be the difference between the two endpoints. Remember, this part here, the reaction is controlled by the excess iodide, but this part here in the blue, that's solely controlled by the excess chloride. So if I know how much it took to get all of the Ag consumed in this part, then all I got to do is subtract it for the second part, for the second endpoint. So we have 47, what are the difference between the two endpoints? 47.41 minus 23.85, that's 23.56 mils. So the number of moles of Ag that were required to react with chlorine is really 0.0845, which is the molarity of the Ag solution, times the amount of volume that was needed for that section of your curve, which was 0.02356 liters. Now, that equals 1.991 times 10 to the negative 3 moles. And remember, again, it's 1-to-1, so if we know that's how much Ag plus was required for that section of the titration, then we know that's the same amount of chlorine that reacted. So all we do is put that number of moles, 1.991 times 10 to the negative 3, divided by the same volume, because it's the same unknown solution. So divided by 0.04000. That would give you 0.0498 molar of chloride. Alright guys, that's it for the titrations video. I'm going to pick up with buffers in the next video. We haven't done a lot of problems in this one, but realize that you, like I said before, you need to do problems on your own. But it is your responsibility to expose yourself to as many problems as you can to try to do well on your third exam. Alright, talk to you later.